Hello students, very good morning. See, we are discussing today BSc semester 5th mathematics unit 2nd, that is linear transformations, in which we are proving one theorem. That theorem is, the statement of theorem is, let U and V be the vector spaces over field F, and F is such that U maps over V be a linear mapping, then F is 1 to 1 if and only if kernel of F is equal to 0. Let me explain you this theorem first of all, that U and V both are what? They are vector spaces and they are over the field F, and the mapping is defined as F is such that U maps over V, it is the linear mapping, and then F is 1 to 1 if and only if kernel of F is equal to 0. So, here the proof starts. Let kernel of F is equal to 0, then we have to show that F is 1 to 1. What we have to show? If kernel of F we are considering it is equal to 0, then we have to show that F is 1 to 1. So, let alpha comma beta, these are the vector elements we can say, because it is taken from the vector space, that is U. So, alpha comma beta is element of this vector space U, that is why alpha and beta both are vector elements. Be such that f of alpha is equal to f of beta, then f of alpha is equal to f of beta, it implies that f of alpha minus f of beta is equal to 0 dash, where 0 dash being the 0 vector of what? V, because U is maps over V, it is linear mapping of U over V. So, f of alpha minus beta we can write, this f of alpha minus f of beta can be written as f of alpha minus beta, that is equal to 0 dash. It implies that, what it implies? That alpha minus beta is element of kernel of F. It implies that alpha minus beta is element of kernel of F, because the function this is the domain part. So, this domain is element of kernel of F. So, alpha minus beta, it implies that alpha minus beta is equal to 0. What it implies? That alpha minus beta is equal to 0. It implies that alpha is equal to beta. If we shift this beta from LHS to RHS, then it will become alpha is equal to beta. Hence, F is 1 to 1. So, it is proved by taking this. What we have taken? Kernel of F is equal to 0 we have taken, and by this we have proved that alpha is equal to beta. So, it proves that it is 1 to 1. Now, conversely, we have to proceed. Means here we have taken kernel of F is equal to 0 and we have proved that F is 1 to 1. Now, we are taking F is 1 to 1. Conversely means what? We have to go in the reverse order, which was taken there in first part. It should be proved here in converse of this theorem. So, we will, why we are doing so? Because we have to prove that if and only if condition. Why we are doing? Because we have to prove if and only if condition. In this case, we have to take the converse part also. Means f is 1 to 1 is now we are supposing. F is 1 to 1. Now we are supposing. Then we have to show that. Now we are going in converse manner. That's why we have to show that kernel of f is equal to 0. So, let alpha is element of kernel of f. One element alpha is considered as element of kernel of f. Then f of alpha is equal to 0 dash, but we know that f of 0 is equal to 0 dash, that we know already. So, that f of 0 is equal to 0 dash. It follows what it means if f of 0 is equal to 0 dash. So, this 0 dash can be written as f of 0. So, f of alpha is equal to f of 0. It implies that alpha is equal to 0, f is 1 to 1. What it is? Because f is 1 to 1, that is why we can say that alpha is equal to 0, because we have proved here 1 to 1. So, alpha is equal to 0. It shows therefore, kernel of f is equal to 0. Kernel of f is equal to 0. So, this is the converse part of this theorem, and this theorem is proved. It was asked few times in Vikram University. This is important theorem as the examination point of view. Now, see, One definition I am explaining, isomorphism of vector spaces. Its definition, let U of f and V of f be two vector spaces. These are two vector spaces over the same field f. Then a mapping f is such that U maps over V is called an isomorphism. What it is called? A mapping of U over V. F is such that U maps over V is called an isomorphism from U onto V. From U onto V if first condition f is 1 1, second condition f is onto, and third condition f is linear. So let us see what is 1 1. F is 1 1, that is if alpha comma beta is element of this vector space U, means these are the vector elements, then alpha is not equal to b, it implies that if alpha is not equal to alpha is not equal to beta, it implies that f of alpha is not equal to f of beta. Equivalently, we can say that f of alpha is equal to f of beta. It implies that, suppose we are considering that f of alpha is equal to f of beta, so it implies that alpha is equal to beta. This is only the condition for f is 1 to 1. Now, f is onto. Let us see what is onto. F is onto, that is for each vector alpha dash is element of V. We are considering alpha dash an element related to vector space V. That is why it is also vector element. There exists, it is the symbol of there exists, a vector alpha is element of U. If alpha dash is element of V we have considered, so there exists a vector alpha is element of U such that f of alpha is equal to alpha dash. Means what? Its image is situated here. Means the image of U, the image of element of U is situated in V. The image of element of U is situated in V. It proves this, that f of alpha is equal to alpha dash means image of U is situated in V, that is known as f is onto. This defines that f is onto. Now, third point, f is linear. That we have discussed many times because we are discussing linear transformations, which is our topic. So, f is linear, this we have discussed a lot of times, that is f of a alpha plus b beta can be written as a f of alpha plus b f of beta, where a and b both are the elements of field, means these are the scalar elements. This is the element a comma b is element of f is field there, and a and b are scalar elements. Alpha and beta both are the elements of U. These are called vector elements because it belongs to vector space U. Now, also then U of f and V of f are said to be isomorphic vectors. What they are told? They are known as isomorphic vector spaces. That U of f and V of f are said to be isomorphic vector spaces, and symbolically we write U of f is isomorphic to V of f. Means the vector space V of f, what it is called? It is called that vector space V of f is called the isomorphic image. The vector space V of f is called the isomorphic image of vector space U of f. See, what is the linguistic definition? We can say linguistic representation for this symbol, that the vector space V of f is called, isomorphic image. This is the symbol of isomorphic image. Isomorphic image of vector space U of f. This is only the isomorphism of vector spaces. So, this definition we now understand, and now we are able to do the theorems also related to isomorphism of the vector spaces. In our further lecture we will discuss that. And thanks a lot for watching our channel. Please do like it, subscribe it and share it.